For those of you who are familiar with how our program and our add-on modules work, are probably already aware of this. For those of you who don't, for 2D and 3D structural analysis and design, our main program is the MasterFrame, and this is essentially where all of the modeling, loading, and load combination can be generated according to the various standards. And here we can do a full analysis of our model, deflection, internal forces, stresses. We also have VM integrations included in the MasterFrame, such as with Revit or Tekla structures. And this is all within our MasterFrame itself. And when we talk about add-on modules, today we will use a MasterKey concrete member design and MasterKey concrete slab and wall design. These are what allows us to do design according to the standards. So here we will specify reinforcement in our concrete elements and check them for the design requirements. Okay. So let's go back into the MasterFrame. So this is our main program, MasterFrame. So I'm not going to spend any time modeling today to save time for getting into the details of our concrete design modules. We have several videos online that go into the details of modeling, so check out our channels for that. So to begin, I went ahead and modeled a very simple structures here. We have our column members, just rectangular elements. We have the same with the beams here. We have a couple of surface elements defined for slab and some shear walls. And the thing to notice is that we have some ribs defined as well. So 1D or line elements, I don't know if this is 2D. Yeah. So 1D or line elements that lie in a finite element surface are deactivated when the surface is formed and only used as lines, such as for the boundary of a surface. However, using the attach beam option, we can select and reactivate any elements inside the surface as an attached beam. When a beam is attached to an FE surface, it is assumed to act compositely with the FE surface. Thus, it is assumed that there will be shear transfer between the beams and the slab. What is nice about the attached beam is that we can define where the rib is exactly placed in comparison to the surface that it is related to. There are 3 options to position the beam relative to the FE surface. What you can also do is to use combined beam plate results. With this option, the axial force in the FE surface is used along with the offset of the centroid of the beam element to calculate the bending moment in the beam. There are also options to define the width of the concrete flange to be used when considering the beam cross-section properties. So it is nice that the program has this attached beam option, which is used quite often for concrete members. Okay, I went ahead and applied some loads here already. So we have our typical loads, dead load, live load, and we have a small wind load. So we have full area loading, full surface area loading, and we have some line loads and the small wind loads as well. We can also take a look at our different load combinations that were or load cases that were generated. If we go into our load cases, we will see here our different load cases. So we have dead plus live, ultimate, dead plus live service, live only, dead only service, dead plus live plus wind, ultimate plus service, and dead plus wind, ultimate plus service. The load cases have been generated according to the Eurocode using our auto generate function. And if we go into our load combination tab, then we will see here all the different load cases with their combination factors that the program used. Okay, with that, we can go ahead and run our first analysis. So static analysis and spectrum analysis. And we see that it solves very quickly. Okay, let's look at the graphical result. So this is our analytical model, including our finite element meshes. So let's quickly check the deflection first to see if our model works as expected. So in that plus live load case, so this is the load case selected. In that plus live load case, the top node of the model moved down with 0.9 millimeter and deflect with 5 millimeter in the x direction. But of course, we can see the result in other load cases as well. So we can select other load cases, or we can see the maximum and the minimum values by selecting one of the envelope result, envelope ultimate, envelope service, or envelope all. But we can not only look at the deflection, but also the member internal forces. Maybe we want to take a look at our bending moment. Bending moment, sorry, with values. Bending moment diagram, or shear force, for example. And we can always increase this diagram to make it a little bit more visible, and you can print this off. And if you go into the shell element tab, we can see the colored shell results as well, such as the displacement, membrane forces, wood and armor moments, and we can check the stress components as well. Okay, so all work as expected. So basically, that is the extent of the MasterFrame. So for structural design, concrete, steel, timber, etc., this is where our add-on modules come into play. You can find all the design add-on modules under the design menu. And let's go and design concrete beams and column first. Okay, the first screen which appears is the default basic data. Setting the basic data and defaults is the key to using the MasterKey concrete member design. These settings are used for beam curtailment, auto design, labeling, etc. There are hundreds of common and structural element specific settings here. The good news is that we can override the default values with our current settings, and all the following projects will use these values as default, or we can save the current settings to file and use it in a following project. Okay, just quickly review the settings. So let's start with the common. For example, under the concrete, we can specify the aggregate size and ask the program to auto-calculate the code theta for maximum shear capacity. Under reinforcement, you can set your reinforcement steel grade, which is 500B for both the main bars and then the links by default. Moving on to the beams, under the concrete, we can set the concrete grade for beams. By default, it's C2530. I'm happy with that. It is important to note that when we created the concrete elements in the MasterFrame, we haven't specified the material grade for them. By selecting the concrete section type, only the elastic and shear modulus have been assigned to the member, so that's why we have to specify the concrete grade here at the design stage. Under the cover to links, we can specify the covers along elements or along members. We can use different covers at each faces. The MasterKey concrete member design can auto-design the members and propose a reinforcement. Auto-design settings allows us to set the minimum and maximum bar parameters for automatic design. We can specify the mean and max bar diameters, minimum number of link legs, minimum and maximum longitudinal pitches. When the concrete module auto-design the beams, it is also does the curtailment to provide you with proposed reinforcement. For the curtailment, the program uses several detailed rules and settings. The most important setting is the beam curtailment style under the detailing main bars. So the beam reinforcement can be detailed in one zone, same reinforcement all along the beams, no curtailment, 2 zones, left and right zone reinforcement, or 3 zones, left and right zones, and the middle zone reinforcement. And the 3-zone design has 4 curtailment methods. Simple only method, using the simple only method, the beams are curtailed to the BS 8110 simplified rules only based on the span ratio. Detailed method, using the detailed method, beam are curtailed to the bending moment diagram. Detailed plus double, beams are double curtailed to the bending moment diagram. This is the method which the program uses by default, and we have a detailed plus simple, beams are curtailed to the bending moment diagram, and the BS 8110 simplified rules. Okay, and there are some other settings as well. So, for example, we can allow only one set of bars per zone. For example, the program can auto delete the short mid bars if the mid bars are shortened than the 30% of the span, and we can specify a minimum span, and the beams which are shortened than this value will be designed with 1 bar zone. There will be no curtailment, and this is only for single span beams. Under the detailing end of beam, we can control how the end of the beams will be detailed. For example, we can set that the program always uses bob and bars, even if the support width doesn't require it for anchorage. We have some detailing options for the links as well. Under the link options, we have an option to set. We have options to set to use, for example, 2 equal size links instead of 1 large and 1 small internal link, which is usually used in case of 4 legs. Or we can use open links with closer, or we can use single leg internal links, and etc. Okay, so let's see the columns. Again, under the concrete, we can set the concrete grade for column. Under the reinforcement, we can specify the cover, slenderness. Yes, slenderness is a critical area in the operation of the program for column design. First of all, the program needs to know whether the frame is braced or unbraced in each axis. And for Eurocode design, we can use the BS BS8110 to calculate the LO embraced columns, and we can calculate the biaxial bending with simplified biaxial bending formula. Okay, under the auto design, we can see similar options we have seen before the beams too. So we can define the min-max diameter and the distance. And we have a few options to control how the program will detail the columns. So for example, in columns where column and dimension are different for each lift, then the program can use splice bars instead of crank bars. For example, we can use single leg internal link, or in circular columns we can use hoops instead of a helix. Okay. Yes, the MasterKey concrete member design can also design path foundations for column bases. And here in this area, we can find the settings and options for this. However, at this time, I'm gonna not cover this. Okay, so let's save the values, or accept the default values. For now, the program detailed all the elements and automatically checked the proposed reinforcement against the design requirements. I'm gonna select one of my top beam first. Okay, so on the left side, you can see the currently selected beams elevation with the proposed reinforcement. Below, there is a bending moment diagram. The blue hedged diagram shows the redistributed envelope moment diagram, while the red line represents the capacity envelope of the member. In case of any failure, the appropriate area of the diagram will be highlighted in red. You can switch to the detailed beam design and dimensional check with this button. So if you are interested in the detailed calculation, you can switch to this view. And below this area, there are the editor tabs. Using the option of the editor tabs, we can manipulate the design as required. Well, let's see how we can manipulate the longitudinal reinforcement first. The main reinforcement diameters, numbers, and lengths can be changed either graphically on the beam elevation here, or using the options of the editor tabs down here below. So for example, if we prefer a smaller diameter main reinforcement, then we can just simply select the bar set here. And yes, the selected bar and its label are highlighted in red. Okay, by clicking on the associated item in the bar label, we can change the bar quantity and size. So the left mouse button increases and the quantity or size, while the right mouse button decreases. So for example, let's use 20 mm bars. So I just simply click on the diameter with my right mouse button, and I then change the diameter to 20. So we can see that now the middle portion of the beam is failing. So we need definitely more bars. So I'm gonna add one more bar to this bar set. So I'm just simply click on the number of the bars with my left mouse button and increase the number from 2 to 3. And now you can see it works now. In the end zones, I also want to use smaller bars, so I'm gonna decrease the size first, 16, 216 works, 212 don't, so I go back to 216s. We need the 260 bars, and I'm gonna do the same on the right side as well. On the graphical area, we can also change the bar lengths. So with the left mouse button, we can drag and release the free end of the selected bar. So if you want to make it shorter, then we can just drag and drop. And of course, the program intelligently applied the minimum overlap between the bars. Okay, looks good. The selected bar set can be also manipulated, as I mentioned, using the beam data tab. So we can change here the number of the bars, the diameter, the length of the bar, etc. On the beam data tab, we can also add new layer of reinforcement as well. So if you want a second layer, we can add a new one, and we can move the selected bar set to there as well. Okay, let's move over to the links. So once we select the links and nib stubs, the program switch to the shear diagram. This table defines the links in the beam. So we have a total of 7 zones. We have 3 left zones, 1 nominal, and 3 right zones with the input of each individual zone. So currently, we use only the nominal links all along the beam, which are 2 legs of 10 mil links at 250 mil. So we can try going down to 8 mil links, and it's still work. So let's try and increase the pitch to 300 mil. The design still works, however, we have dimensional arrow, and this is indicated here on this status bar. By clicking on it, we can jump to the dimensional checks, and if you scroll down to the bottom, then here we can see that the maximum longitudinal distance is 264 mil. So we have to go back to the 250 mil to create to clear this error. Okay. So let's move onto another beam. If we select one of the rib members, then we will see here in the section area that the program intelligently created the proper T-cross section, even though we only define the cross section, define the cross section as a square section, as you can see here on in the graphical area. This is because we defined these members as attached beam to the slab and selected combined beam plate results. Okay, let's see the column design. I'm going to select this internal column. As we can see, the user interface of the column design is way simpler than the beam designer and than the beam design interface. The beam elevation and diagram area is replaced with this detailed design output results with the column section graphic. This column section graphic only shows the cross-section dimensions and reinforcing details, but it is not an interactive graphic. So all the manipulation can be done on the column data tab down here. The editing area is very straightforward. So we can change the diameter of the corner reinforcement, the number of the diameter of the number and the diameter of the side reinforcement. So if you want, we can add an additional sidebar, 16 mil sidebar for each side. If you want, we can use asymmetric reinforcement as well. So we can do this as well. And we can also change the links, diameter, and distance, and also the number of the legs in the two directions. The restraints and bracing arrangements are calculated from the frame geometry and global values set in the basic data and defaults. Okay, so this is our beams and columns, column design. We have an option to scan all members for design failures. It stops at the first failure. So you can see we have small issues here. So we need just to simply, oops. Only need just to simply move this a little bit, and it works now. And if we click on the Find Next Failing Member button again, then it will go to the next failing member. Okay. And of course, we can export all the beams and columns with the reinforcement to AutoCAD for further detailing. So I'm going to save this as it is now, and I move forward to the slab design. So under the design menu, so we have another option called concrete slab design. The first thing which appears is again the basic data and default screen. On this dialog, we can set the usual design parameters such as reinforcement grade, covers, orientation, and this dialog allows to specify the default bar diameters and spacing. So for example, this is our basic rebar. This is our basic rebars. Then at 200, and we can specify the peak zones, etc. I'm going to accept the default. Okay, just a few words about the philosophy of the design process. So in the slab design module, we have three main reinforcement tools. Basic reinforcement, first one, apply. The basic reinforcement is to apply generally to an fill surface. Peak zone are intended to provide enhanced reinforcement in zones where peak bending moment occur. Peak zones provide options to define reinforcement in two orthogonal directions in either the top or bottom of the slab. Strip reinforcement are intended to provide enhanced reinforcement in strips where higher bending moment occur along lines, for example, within column strips in slabs. The strip reinforcement provides options to define reinforcement in either the top or bottom of the slab, and also whether the reinforcement is orientated parallel or perpendicular to the strip lengths. Strips provide option to define reinforcement in one direction only. So when first designing the reinforcement for a slab, the first step is to define the basic method of the reinforcement with the basic reinforcement. The first round of the design check will give a good idea of where the basic reinforcement will be enough and where we need to apply some additional reinforcement, such as a peak or a strip reinforcement. Then we can assign the peak and strip regions to the areas where we want to have a refined reinforcement design. So start and add a new basic reinforcement first. Okay. So straight away we got some design based on the basic reinforcement, which is 10 and 200, both at the top and the bottom, all over the whole slab. So how is this reinforcement performing? So not very well, and at the moment, as you can see, to clearly see the failing zone of the slab, we can ask the program to draw the counter surfaces of the unity ratio. So this is top view. Sorry, yes. So this is the hugging moment in the either in either the x or y direction. We can see exactly where we need to add the additional top reinforcement. So the middle of the slabs works work well. However, we need to add some additional reinforcement in the column strips and around the column heads. And this is the maximum unity ratio for the sagging moment. So this is the bottom steel reinforcement unity ratio. Okay, let's start designing the bottom steel first. So as you can see, the bottom steel is failing in both directions. To save time, I'm gonna change the basic reinforcement, as the default 10 at 200 reinforcement doesn't work very well on big area of the slab. By changing the bottom reinforcement or bottom bars, sorry, I need to move this up a bit. So by changing the bottom bars to 16 mils, you can see that the bottom reinforcement just works. So we only need just to refresh the diagram, so you can see graphically and also here in the detailed design that now the bottom steel work. Okay, let's move to the top reinforcement. So this is our top reinforcement unity ratio. First, I'm going to again change our basic reinforcement to get our basic reinforcement work on the majority of the slab. So by changing the top bars in the direction 1 from 10 mils to 16 mils, then you can see now our top steel is only failing around the column heads and the corners. And now I'm gonna add some additional peak reinforcement to the column heads. So let's move to the peak reinforcement. And instead of adding the peak reinforcement zones individually, in add multi-mode, I'm gonna window all the points. I'm gonna add the default peak zone reinforcement in one go to all the points. Okay, so here in the list, here you can see the 9 peak zone reinforcement. I just add it to the slab, and you can see the unity ratios or each of the peak zone. So if you select any of the peak zone, then you can see the parameters here. So the the peak zone reinforcement added to the basic reinforcement. So this is, you have an option to replace the basic rebar in the zone of the peak reinforcement, but by default the peak reinforcement is an additional reinforcement to the basic reinforcement. And of course, this is a top reinforcement. Okay. Interesting. The detailed design still shows some problems. However, I can see any issues on the graphic. Okay. Anyway, there should be some very tiny area which is still failing. I'm just cannot see it. Anyway, I'm gonna accept this because it's it looks good for me now. Okay, let's overview the reinforcement we got. So if we so we have an option to draw the rebar areas. All yes. So this is our bottom direction one. So we got 60s at 200 post direction, and this is our top steel direction one top steel. So we have the basic, the cyan blue represents the basic reinforcement, which is 16 at 200, and we have the peak reinforcement area, the green peak reinforcement area, where we have the basic plus the additional 10s at 200, and this is our direction 2. Okay. Now we're gonna do some punching shear design very quickly. So we have the last option here in the slab designer is this the punching shear design. The punching shear design is very straightforward. We add a punching shear check and we click. We add the punching shear check and we click on the point to which we want to apply that, and it automatically designs any punching shear reinforcement if required. In Add Multi-Mode, I'm gonna window all the points and add the punching shear check on all the locations. And let's look at what we got. As we can see, some positions require additional punching shear here and here. Some positions don't. So, for example, these wall end area doesn't require punching shear reinforcement. If additional punching shear reinforcement is required, then the program shows you the proposed layout. So you can see the proposed layout. By default, the program uses 12 mil bars, and the bar arrangement is equally spaced on perimeter. You can change this, of course. So we have some other shear rebar layout as well. So let's say that our slab is totally designed, you can also export your sub reinforcement to the Excel for DVG drawing. So I'm gonna close the slab reinforcement design module. And the last thing I would like to show you is the concrete wall design. Okay, as usual, the first thing that appears is the basic data default. So we can set our steel grade and cover, the basic bar sizes and spacing, design method for the shear wall, the same thing for the coupler beams as well. Okay, this is the user interface of the concrete wall designer, quite similar to the concrete slab designer. We have object list for piers and coupler beams, and we can switch between those. So let's design our first wall. With the plus button, we can add a new wall pier to the object list. The next step is just to select the FE surface, and we have to draw the pier zone. Now I'm gonna design the whole wall. Okay. Okay, let's have a quick look at our inputs. So under the geometry, we can see the position parameters of the zone, which can be altered. Design methodology is the most important area, and the design method of the pier subdivision that you choose here might affect the accuracy of your design. By default, the program uses the equal strips fixed width method. This method splits the zone into 1 meter with strips by default, starting from the left and right with the makeup middle zone. In the graphical area or graphical drawing here, we can see the actual strips. We can see that even though we selected, or even though we use the default 1 meter with fixed strips, the outer strips are slightly narrower, while the innermost strips are somewhat wider than 1 meter. And this is because the program chooses sensible design strips width with the rounding to the rebar spacing midpoints. But of course, we can choose other design method as well. Okay, looking at the bars, for vertical bars, we applied 16s at 200, and it is set to use the same rebars all across the strips. But if you want, you can use different vertical bars, split strip by strip, and and for the horizontal bars we have 10s and 10s at 200. And of course, we can see we can draw the rebars to the wall. So this is the vertical rebar, 16s and 200. You can see here in the legend. This is our horizontal bar, 10s 200, and of course we can see the unity ratios axial with moment. So you can see the unity ratios here. By using the auto design option, we can auto design. We can ask the program to optimize the reinforcement for us. So if you click on it, then the program will optimize optimize both the horizontal bars and the vertical bars. You can see here the updated unity ratios now, and if you see the if you look at the reinforcement, then this is what we got. So this is the vertical reinforcement, tens at 350 vertical, and horizontal tens at 300. Okay. For the other wall, I'm gonna quickly just auto-generate the zones in one go. So using the auto-generate option, I just simply, sorry, the window is here. So using the auto-generate option, just simply windowing this wall, and if I click generate, then you will see that the program created two wall pier zone, one at the left of the opening, and one on the right of the opening, and we have one coupler beams here as well. So we technically generated 3 zones. So drawing the reinforcement, all the reinforcement for all the generated zones, then we can see that the program applied the default vertical reinforcement, which is 16 at 200, and the horizontal reinforcement is 10 at 200. By looking at the unity ratios, then we can see that all the wall works with the default reinforcement arrangement. However, we can do some optimization. So by selecting the new wall piers, I'm gonna auto design these zones now. Okay, it's ready. Watching the maximum unity ratio, we can see visually that all the wall works. So let's take a look at the applied reinforcement. So this is our new vertical reinforcement. On the left side, we got the same tens at 350. On the right side, we got the 12 at 300. And let's see the horizontal reinforcement. And for horizontal reinforcement, we got the same tens at 300 for in both sides. Okay, and let's move over to the coupler beam. We check the reinforcement, then we can see that the applied default reinforcement is 2 number of 10 mil tops and bottom bars, and 2 number of 10 mil sidebars. So this is our horizontal reinforcement. We can see here in the graphical area or in the drawing area, but we can also see visually on the 3D graphics. So this is what this cyan blue means. And if we switch to vertical, then we can see that and the applied shear reinforcement is 2 number of 10 mil legs at 200 mil. Okay, let's do some optimization. So we can go down to the bars and we can change it manually, or we can again ask the program to auto design the selected object or the selected beam. Okay, and what we got, horizontal bars remain the same. However, the vertical the shear reinforcement has slightly changed. So now we have two number of 10 mil legs at 400 instead of 200. Okay, so that's it. So this is the wall design. In the MasterSeries, and of course we can export the reinforcement, the design reinforcement to the XFDVG AutoCAD drawing. So this is the concrete building design in the MasterSeries. In a nutshell, of course, we have some other tools as well, so we can not just calculate the concrete slab reinforcement, but we have options to calculate long-term deflections and crack controls as well. So we can calculate the crack width as well. There is an option to calculate pi caps, and as I mentioned, the concrete beam, the concrete member design can calculate the path foundations as well. Okay. So, ladies and gentlemen, I would like to thank everyone to attending today. I hope you enjoyed and learned in this presentation, and see you on our next webinars. If you have any further questions, you can get in touch with us on our usual channels. And if you want to try out the software, just go to the MasterSeries website, fill in the form, and request a free trial. After the webinar, please do not forget to fill in the short 1-minute survey to let us know how you like the webinar. Okay, so ladies and gentlemen, again, thank you very much for attending, and have a great day.